We'll begin our third and final part of our probability intro lesson by looking at the probability sum rule. Now, the probability sum rule includes both events occurring, that's an and situation, and if we're looking at a Venn diagram, that's why I have it highlighted in green, because that would be overlapping. But the probability sum rule also takes into account an or situation. That would be the U-like symbol, also representing union, and that would mean that it could occur in A only, it could occur in B only, or it could occur in A and B at the same time. So the whole blue section here is what we're looking at. If I wanted to look at this a little more in detail, and I said, okay, I have an event and whose probability event who only lands in A, so only this part right here, and it happens to occur 1/4 of the time. And I have an event that happens to be in B only, which will only be this part, and that happens 1/4 of the time. And I also have an event that happens 1/4 of a time, but it occurs in both A and B. If I was to try to figure out what's the probability of occurring to be either in A or B, I would add 1/4 plus 1/4 plus 1/4 and come up with 3/4. But if I actually did the math up here, the probability of A would actually have been 1/2 because it's 1/4 plus 1/4. The probability of B would actually be 1/2 plus 1/2, which means it's 1, and that's not the correct answer. And the reason for that is I've double counted the 1/4, so what I would want to do is subtract the 1/4 from being double counted, and that's how I would get my 3/4. I don't have to worry about this if the events are mutually exclusive. If literally there's an event that occurs and 1/4 of the time, and an event occurs at 1/4 of the time, and they don't overlap, it's going to be 1/2 because it could be here or here, and in this case I would have 1/4 plus 1/4 equaling 1/2, and the reason for that is I will be subtracting 0 because there is no overlap, and I'll come up with a probability of 2/4, or in this case 1/2. And just because I see this right now, let's just highlight this in green to represent that section right here where they both occur. Let's take a look at conditional probability. Conditional probability is a kind of a takeoff of dependent events, because we're basically saying what is the probability of B given the probability of A. And so what I need to do here is first understand is the first letter of your probability notation, that's going to be the event you're trying to find, the probability, but the second one, event A, that's the one you already know. And so what you do is you would take your whole entire overlapping, assuming that's not 0. I mean, if it is 0, it's still going to be 0 over something. But you take that whole entire probability of just where they overlap, that would be this section right here, and then you would go ahead and divide it by just the probability of what occurs in A, because we already know it's occurred. We don't have to worry about what happens in B or other events that don't apply. I have a great example for that literally once I move the screen up. But before I get there, you're going to see occasionally I might use the letter N instead of the letter P. And the reason for that is a lot of these formulas can be reused as counting formulas. And so the way we differentiate between being a probability and a counting is literally P for probability, N for the number of occurrences. And so this could have been written as N of A or B equals N of A plus N of B minus N of A and B. And I have an example down below that will represent that situation. Just remember, probabilities have to fall between 0 and 1. So all the answers, all these numbers here would have to be between 0 and 1. Counting, that's, integers. You can have like 30 of this and 40 of this and maybe 5 overlap, and then you would say 30 plus 40 minus 5 is 65. And that would be a way that you could figure out maybe the number of ways that A or B can occur. Let's actually look at these examples of formulas in action, okay? And so we're going to move right to this one. In fact, I'll stop right here because my first example involves algebra roulette again, and it's a conditional probability. Because what I'm basically saying is we're going to take a spin, and I would like to find the probability of B being a red, that red appears when I spin, given that I know that the value happens to land in row 3 Again, row, column, you know, if you're looking at it this way, it's a row. If you look from the perspective of reading the numbers, it's a column, and we're going to stop talking about that now. I could have literally gone through and done all the reds in row 3, which is 8 out of all 36 possibilities in the sample space. And then I could have also then divided that by the number of elements in the sample space that happen to be in row 3, so 12 out of 36. That's a lot of work when I could have just basically said, well, there's 12 numbers in the row. That's all I'm looking at this point. All right, I've eliminated 24 numbers, so let's just look at the 12 numbers and realize that 8 of them are red, and I'll still come up with the same result if I had done this, and that works out to be 2/3. So that was the probability of picking a red once I knew that I had row 3. Okay. Let's take a look at a counting problem. We're not going to do probabilities, we're going to do counting. So I'm going to rewrite these with ends instead. And it says here that I have 20 secret agent stick figure novels that are being written, and they've all been read. So it's not like a case I've only read 18 have been read or 14 read. I'm telling you right now up front, all 20 books have been read, and it's been read by 2 individuals, Aaron and Bob. Now, Aaron had read 17 novels. He says, I've read 17 novels. And Bob says, oh, I've read 13 of the novels, and they find out that they've read all the novels between themselves. So the question is, how many novels had been read by both individuals? Remember, there's only 20 books total. So if you're going to create a Venn diagram, all right, you'd have to say, well, 7 were in A only, 3 were in B only, and then 10, because all 3 numbers have to add up to 20, would have been shared. Well, let's show you how I would have actually done this mathematically, okay, not with just a Venn diagram and trying to figure out the numbers. So here I would have gone the number of A or B, which in this case is 20. Either Aaron read this book or Bob read this book, and remember, it could be Aaron and Bob, and that's a place for that literally right here. So 20 equals the 17 books that Aaron read plus the 13 books that Bob read. Now I just subtract the overlap because you can't read 30 books when only 20 were made, so then 10 had to be read by both. So you don't have to guess the Venn diagram, you can actually compute it out. Let's take a look at another example, another conditional probability, except this time we're going to do it with probability, but we're going to also do it with ends as part of the formulas to show you that, you know, there's a neat way to mix and match. If I'm going to try to figure out the probability of rolling a black 1 when I do 2 standard dice at the same time, a black and a white dice, but I know that the sum happened to equal 5. I could do the probabilities, but in the end, what am I doing? I'm counting up the number of sums of 5 that included a 1. So instead of saying that there was 1 out of 36, I could just focus on that there was one roll that was black and had a sum of 5. That's the 1-4. And then I just say, okay, how many sums of 5 were there total in the list? And since you could do a 1, 4, 2, 3, 3, 2, 4, 1, there were 4 numbers. Done. 1 out of 4. So as you can see, we may use counting formulas instead, or number of occurrences, to determine our probability, and not always going back to the actual probabilities themselves. And finally, here we go. What is the probability that a card randomly selected from a standard deck is either a queen or a heart? Now, if I look at the probability of getting a queen, I could think of this as the number of ways, which is 4, 1, 2, 3, 4, and that's 4 out of the possible 52 cards, or 1/13. Here I have the probability of heart. There's 13 cards, ace or king, or 1/4 of the deck, because there's 4 suits, and it's 1/4 of the suits. And so I would say 4 50 seconds plus 13 50 seconds is 17 50 seconds. And yet, when I count, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I don't get that number. It's because this one and this one is counting the Queen of Hearts, that card, twice. Each one is counting it once, therefore a total of 2 times. That's 1 too many times, and that's why I'm going to subtract one of those extra Queen of Hearts. And that's why when you go 4 50 seconds plus 13 50 seconds, and you subtract 1 50 second, you get 16 50 seconds, which is what I said, and that reduces to 4/13. Our next page begins by looking at what are called two-way frequency tables. And that's a table that describes frequencies, that would be these numbers right here, of two categorical variables. We've got our different rows, A, B, C, D, in this case a grade, and columns, which is Mr. Aardvark, these are the numbers this way, and Mrs. Zebra. And they're going to come from the Spurious University's Intro to Underwater Basket Weaving course. And we're saying of those that have taken that particular underwater basket weaving course, 78 students received an A over time. 52 students were not happy with their grade when they were finished. In Mr. Aardvark's class, we had 551 former students, and Ms. Zebra had 203 students. And I've done all the totals to make it a little easier for us, but there's 754. And what we're going to do is we're just going to randomly select one student, and maybe they're going to take a survey. And we're going to figure out the different probabilities. Unfortunately, to be able to compute most of this, I'm going to have to see the table, and I would like you to see it. So that's right, I am going to have to zoom out, and you'll just have to follow along on your sheet, but at least we'll be able to see all the numbers. So we'll start there. And we'll begin by first doing the probability of A, which is, in this case, getting an A. And so what I would look at is how many students got an A, and that would be 78. And then I would divide by how many students there were, and since I said there were 754 students, they all equally likely to be selected, and that's 754, I'll just put the 754 there, and we'll make ourselves happy. And that's pretty much it. The next one says we're going to take the probability of Mr. Aardvark. Okay, so now Mr. Aardvark has 551 students. We could add up all these numbers right here and just say that's 551, and again that would be out of 754. This one is our little AND event, so I'm going to write this in AND. This means AND, which means we're looking for overlap. Okay, and for that I am going to look for Mr. Aardvark. There we go, and getting an A grade. And so what I do see is I see that there are 57 students out of 754. So if I'm going to figure out what the probability is for A, and then again, this is an OR situation, all right, which means that it could be either one, either. I can't double count 57. See, when I did this 78, I got the 57. When I did the Mr. Aardvark and got the 551, I included the 57. So I could, and I'm going to write this in, again, a fine print, I could just manually say, okay, I'm going to take my 57, and I'm going to take my 21, but then I'm going to go down the line. I'm going to go 133, and 228, and 97, and 36, and I'm going to divide that all by 754. But a smarter approach would be to take this one, and this one, and apply the rule back on this page, which is right here on top. That's right, the probability sum rule, where I'm going to do my OR situation based on the probability of A and B and subtract the probability of A and B. And that's exactly what I did for all the steps right here. So I'm going to put this one in red, and I'm going to take literally to figure out this answer. All right, so let's just say that could have been done by going 78. Now, since they're all going to be the same fraction, I'm just going to write it a little differently. I'm going to say take the 78 here, add the 551 here, and then subtract the 57. And if you're really struggling to see what I'm saying here, I'll be nice. 78 over 754 plus 551 over 754 minus 57 over 754. And in the case, in the end, what you should have receiving is the answer to this problem is 572 over 754. So yeah, it'll be kind of a bit of a challenge to squeeze that all in the paper so that you can see at the same time, but we'll do our best. But yep, so if you take this one, and subtract this one, you'll be able to figure out the OR situation. But we're going to use our two-way frequency tables to go back and practice a lot of our other vocabulary terms. For instance, this one does say we're supposed to use odds. Say in favor, it's going to be essentially, let's say I'm successful in picking an A, which in this case, there were 78 students, okay? And that would be, so we'll say this is the success temporarily. I'm going to have to erase that in a moment. But then I'm going to compare to those not picking A, which would be these numbers, okay? And for that problem, I might actually want to do this one first, because picking not A, I could go and say, all right, well, that's 182 and 312 and 130 and 52 out of 7. You know, I could do all that. Or I could just simply have gone, here's 1 minus just the 78 out of 754, which means it's going to essentially be 754 over 754 minus 78 over 754, and that one worked out to be, in this case, 676 out of 754. Well, it's the 76 that I actually want here. So this is the success, this is the sort of like the failure, and so I'm going to say 78 to 676. Now, can all these be reduced? Yes, they can. I'm not going to worry about that. I'm just trying to teach the basics on this kind of stuff. You can feel free to reduce. It's not something that I'm going to worry about. So now we've come across some conditional probabilities, and you'll notice that we have the A first, followed by aardvark, and we have the aardvark followed by A. So what I need to understand is Mr. Aardvark is known. Mr. Aardvark had 551 students. I just need to know how many of those got A's, and that would be 57. This one conditional probability is saying, all right, I know that I got an A. So let me just put the words know here to make it easier for you to realize. I know I have an A. So now I've just knocked that down to 78 students. Again, how many of those are Mr. Aardvark students? Well, 57. So the difference is that when I look at this one, I've narrowed it down to 551 students because I knew it was Mr. Aardvark. But here I've narrowed it down just to 78 students because I have just A students that I'm looking at. Now comes a couple more questions that are left. You'll see that we have just this left. Unfortunately, I think I can, yep, looks like I might be able to squeeze it in here. Just remember this is Mr. Aardvark, and this is Mrs. Zebra, okay? It says, are events A and aardvark independent to each other? So that's what I'm going to be taking up here. The probability of A, then I'm going to multiply it by the probability of Mr. Aardvark, which I'll just say Mr. A, all right? And I have to show that it is equal to the probability of both A and Mr. Aardvark. Well, that's, again, where these particular numbers are really helpful. If I can show that 78 out of 754 times 754, there we go, times 551 out of 754 works out to be the same as 57 out of 754. And if I put this in the calculator, I'm going to find out, yes, it does. Then I can say they are independent. And that's it. That's all you have to do. So it really is important to figure out the two individual probabilities and find also their and situation, their overlap, and you can use that to figure out or situations. You can also use that to figure out if they're independent or not. I have two more follow-up problems right down here. It's a couple more conditional problems. I've learned that students sometimes have struggled with this. And so I just thought a little bit of practice. Again, this one you know that you have Miss Zebra, and you know that she had 203 students, so we'll just put 203 right here immediately. And I see that we're still trying to get A's, and you'll see that there was 21 students. And so with that alone, we had no issues. And then we have Miss Zebra. Sorry, we know that we have A students, and of course I just slid that down right now. Okay. So again, we have our 78 students, but of those students, 21 received A's, which I could, I guess, looked right there, and that's what I get. The reason I'm asking this question and also having it here is one of the reasons I'm bringing this up is the classic argument is, oh, you had this teacher is tougher, and vice versa. Well, I'm going to tell you right now, all the students that got A, didn't matter which teacher they got, it was independent to each other, okay? We didn't have to worry about A's affecting the teacher or the teacher affecting the A's. The reason there were more A's in Mr. Arbor's class is he had more students. That's pretty much it. We're going to do this all over again. The only difference this time you'll notice is that I used a few N's instead of always using P's, and to emphasize that sometimes we're just looking for the number of occurrences. So let's slide this back up here. We'll do a lot of the similar math. Let me remove this from the picture. Let me remove this from the picture. Focusing on Miss Zebra's students, which in this case literally is just there's 203 students. No probabilities are needed here. You're just adding up to 21, 49, 84, 33, and 16. Those that got unhappy grades are these two numbers here, 36 and 16, so a total of 52. Now, who had Mrs. Zebra and also was unhappy in the class? I'm looking for where they overlap, and the one number that overlaps represents the 16 students that had Mrs. Zebra and were unhappy. This one, again, is the OR. So if this is the AND, this is the OR. And I'm going to make my life easier. I'm not going to count up all these numbers and only count that one twice. I'm going to take the 203. I'm going to add the 52, and I'm going to subtract the 16. I'm going to go in that order because that would have been double counted twice, and I would have found out that I have 239 students that either had Mrs. Zebra or did not get a happy grade. If I'm looking for a not situation in this case, well, this one's going to be pretty easy. This is where they did, yes, or yes, success, had Mrs. Zebra. This would be your not situation. The 754, there were 551. Again, let's put that in green. 551 students that did not have Mrs. Zebra. If there were other teachers, we would have to add those up, but there aren't. Now, that was pretty easy. Let's also explain that I could have gotten this number by taking 754 and just subtracting the 203. That was Miss Zebra. That would have been a lot easier if there were multiple teachers, all right? And I just have to deal with one teacher and then subtract them from the group, and I would have this 203. Odds against means, here we go, odds against means I'm going to put my failures to successes, or in this case, my not zebras to zebras. And in this case, my not zebras are 551. Now, I could use the word to, but I can also use a colon, 551 colon, and then we'll say 203. And those look like really lousy colons, so let's put that there, 203. So odds would be, in this case, A to not A, and odds against is not Z to Z. Basically, just change the order. Success to failures, failures to successes. If we see that I have an unhappy grade, I would just narrow this down to my 52 students. Of the 52 students, okay, they're there, 16 had Miss Zebra. If I know I had Miss Zebra, I'm going to narrow it down to 203 students, but again, still 16 students were unhappy and also had Miss Zebra. So if I'm going to try to determine if these are independent events, just like A was independent, didn't matter which teacher he got, well, then I should go ahead and take the probability of, in this case, the unhappy grade, and I will multiply that by the probability of Miss Zebra, and to see if that works out to be the probability of being unhappy along with, okay, having Mrs. Zebra. And so I'm going to do probability, and I'm going to take 203, and I'm going to divide that by the 754. Oh, I've got that in the wrong number. That happens to be Mrs. Zebra. I have to, if I'm going to line it up the way I see it. I mean, I could have put Miss Zebra first in there, so it really doesn't make a difference, but I want to be organized, so if you do come back and look at it, it makes sense. 52 out of 754, I'm going to multiply those together. Well, what I'm going to find out is when I did this is that this does not work out to be the same as 16 out of 754. It's not the same number. It's really close, but it's not the same. And so because this does not equal each other, then we did not prove independence, which is the way, again, I like to think of it. And so by default, they are dependent events. And so I'm just going to give you a little heads up. What I did here is, the way I set this table up is, I actually made these three events independent. So if you got a good grade, all right, A, B, C, it really didn't matter which teacher you had. Mr. Aardvark would always have the same proportion of A's as Miss Zebro, okay? And then for the D and the not so happy grade, well, I just sort of kind of moved one over to the other category. So they're really, really close. But mathematically, they are dependent. So depending on what teacher had, does affect the possibility of your grade, but it's really actually quite negligible. So for all those people that like to complain about their teacher, so there, all right? And then finally, we're going to look at getting a bad grade in Mr. Aardvark, but in this case, it's going to be a probability. So just again, reminder that it's a probability, it's not a number. So what we're going to do here is we're going to write down all the bad grades, which is 52, and then having Mr. Aardvark, there was 36, and 36 out of 52 could definitely be reduced. But if I know I have Mr. Aardvark instead, I'll just notice I only can narrow it down to 551 students, but I'm still looking at the same 36 students on top. We'll finish up our probability introduction lesson by looking at probability and geometry. And for our last examples, we're going to look at a rectangular yard that happens to be 50 feet by 100 feet. And that yard happens to have a circular pool, which emphasizes the phrase diagram not drawn to scale, because the pool supposedly has a 12-foot radius, which makes that 24-foot diameter. And if this is 50 feet, let's say height-wise or lengthwise, that is definitely does not look like 24 out of 50. And then we're also going to have a triangular garden over here, and if this is supposed to represent 50, there's no way 6 feet comes almost to the halfway point. So again, phrase diagram not drawn to scale totally applies here. And a ball is going to come falling in, and it could land here, it could land here, it could land. It's all equally likely, and let's just put a dot there. Okay. What's the probability that the ball lands in the pool? Well, if I'm going to figure out in pool, I'm going to go back and kind of look at my numbers, and in this case, I'm going to look at the total square feet of yard, because that represents my total area. And since that happens to be 50 times 100, I'm going to come up with 5,000 as my, in this case, denominator. Then what I'm going to do here on top is I'm going to take the number of square feet of just my pool, and in that case, we know that the circle formula is pi times radius squared, or pi 12 times 12 squared, and that simply works out to be 144 pi, and I could reduce that, but again, I'm just trying to emphasize how we compute probability, and that's how we would do it. We would just take the area of where we expect it to land, divided by the whole entire area. So if I'm going to do the ball lands in the garden, okay, actually it's not going to change anything down here. Square feet of yard, and in this case, we already know, and oops, that's not very neat. Let's try that. We already know 50 times 100 is 5,000. The only difference now is I have to find square feet of garden, and that's 1/2 times 6 times 8. Base times height in this particular problem, and that works out to be half of 48, which in this case is 24. And, And if you think that's impressive, no, because I'm just looking at what I did and my notes from the last time I did. Now it says, what's the probability that the ball lands in the garden or the pool? Okay. The neat thing about these two events is that these are events, this one and this one are mutually exclusive. Now I know I did say that diagram not drawn to scale, but in this particular case, it's not too often that I've seen a garden and a pool overlap at the same exact spot where literally a garden is growing in a pool. So I think it's safe to say that this part of the diagram may be pretty accurate. And so all I need to do my OR situation, the probability of in pool, and then I'll highlight the letter OR by taking the union symbol, or let's put it this way, I should be putting the pool second just because it's there, and putting garden first. Again, would it make a difference? No. But I would just simply add up the probability of the in garden, which in this case, I'm going to just simply keep 24 over 5,000, and you'll see why I'm still keeping with that number. And then I'm going to add it to the probability of in pool, which in this case is 144 pi over 5,000. And now you understand why I am not going to worry about reducing my fractions all the time, because I like to have a common denominator. And then technically, I should be subtracting the probability of garden and pool at the same time, but we know that probability happens to equal 0, so that really doesn't make any sense to even worry about that. That's the beauty of mutually exclusive events. And so if I just combine them as one fraction, it might look something like that. And our last question says, what is the probability that the ball does not land in the pool? Well, the key here is the phrase not there, so let's emphasize that. So what I think I'll just simply do is I'll just say the probability of not in pool is 1, which in this case might be 5,000 over 5,000, which just basically represents all square feet of yard. Okay, you know what, I'm going to change that a little bit. Let's say all 100% of yard. I like that because 100% is 1. And then I'm simply going to subtract the all landing in the pool, which in this case was 144. So let me put it this way. Probability of in pool, which means I will subtract 144 pi over 5,000 and simply just say, hey, it's 5,000 minus 144 pi over 5,000. And again, if I was reducing, and this is because I'm an algebra teacher, I would have to make sure that I could divide in the a number out of 5,000 and 144 and 5,000, just like I'd have to check those numbers. And with that is the final part of our probability intro lesson. If I could just take a rectangle and draw it better.